Okay.
Great. Great. All right.
So thank you to the jurors for being here. Welcome to the other visitors. And when you're ready, you can take it away. This is going to be the N95 mask with an integrated nasal cannula team.
Yeah, we'll begin. So thank you for the introduction, Carol. So yeah, we're the N95 mask with integrated nasal cannula team. Our project advisor is Professor Carol Livermore, and our group members are Alex Arcasoy,
Conor Byrne,
Elysia Fusco,
Michael Melito,
and Molly Sharpe.
So typically, if someone's wearing a nasal cannula, they have a severe respiratory condition that puts them in a high-risk category if they contract COVID. These people need a more robust protection system, such as an N95 than the cloth face covering recommended for the general public. These people cannot use N95 because the cannula breaks the airtight seal and renders the mask ineffective, and there's no current market solution for this. So this brings us to our problem statement, which is to protect nasal cannula users from pathogens, the team will create a mask with N95 filtration and an airtight nasal cannula integration. So nasal cannulas are used for supplemental oxygen delivery for people who are on long-term oxygen therapy. The key features are that it's connected directly to an oxygen tank, is made of soft polymer tubing, which varies from cannula to cannula and lasts anywhere from 2 to 4 weeks, depending on how often the user wears it. N95 masks filter out at least 95% of particles as small as 0.3 microns in diameter through having an airtight sealer on the face, having 4 separate layers, and utilizing electrostatic attraction. The mask lifespan is relatively short at only about 5 uses or 8 hours, and it's important to note here that the cannula life is much longer than the N95 filter life, and this is something that we considered while coming up with our design.
After talking to experts and cannula users about their needs, the team generated several high-level requirements that can be broken down into 3 categories: performance, comfort, and modularity. First and foremost, the mask cannot interfere with cannula performance and must create a proper seal for the user's protection. The mask should also be comfortable and allow the user to breathe easily. Lastly, it should allow for the regular replacement of both an N95 filter as well as the user's nasal cannula. In order to facilitate the user needs, the team further developed specific design functional requirements. Building the mask from the ground up, since the use case life of N95 material and nasal cannula tubing are different, the team required a reusable body. In order to support the physical insertion of the tubing, the mask should also be rigid. Without making any alterations, the user should be able to insert and remove their own cannula with ease, meaning the mask needs to open and close around an entry point. The team determined that a hinge and latch mechanism would create an effective solution that facilitates both the cannula insertion as well as N95 filter replacement. Since the mask will open and close, the team needs to ensure proper sealing throughout the design, specifically around the cannula entry point. In order to keep the mask airtight, the team introduced foam gaskets and a deformable silicone face seal. While functionality is important, the user's comfort was also greatly considered throughout the design process. Since the target audience for this mask tends to have difficulty expelling carbon dioxide, the team added an exhale valve in the center body component for ease of breathing. While this feature helps users exhale more easily, the team is still concerned with the safety of those around us, and therefore added an exhale valve cover on the outermost point of the mask, protecting the general public just as a normal cloth mask would. Lastly, the team introduced an adjustable head strap with a toggle stop to allow this mask to fit any user.
So here you can see our final product, our working prototype in its glory. So I'm going to go through some of the individual subsystems that Molly just touched on. So on the left, you can see our CAD, and on the right, the final prototype. On the top of the mask, we have the latch, and on the side, we have the elastic strap hooks that the toggle stop and adjustable strap mount to. The rigid body is what all of these components are attached to, and what the cannula seal and face seal interface with. Going on to the real pictures, we have the exhale valve cover, which covers the outside of the mask in front of the exhale valve, which is located on the middle stage of the mask with this little green object. The N95 filter is replaceable and fits between the front and middle stages of the mask, and the gasket seal makes sure that the whole mask is sealed well.
So the base of our design is its rigid and robust plastic body. Now, most importantly, this allows the mask to be reusable, which is a feature desired by those who we interviewed. Next, it allows us to resist tugging from the cannula on the mask. The cannula is a tube that goes over the ears, so if the user turns their head, maybe talks, it could tug at the mask, and a standard cloth like N95 mask won't be able to resist that tugging without deforming. And lastly, we needed a rigid body to be able to support our replaceable N95 filter. To make this body, we decided to use SLA printing because it's great for rapid prototyping, and unlike an FDM print, it's solid and fully dense, whereas an FDM print would be maybe porous, and if you got a hole in the design, it could lead to leaks.
So one of the first challenges was getting a hold of N95 filter material. We wanted to veer away from cutting up a standalone N95 mask, since they come in many different shapes and sizes, and consistently producing high quality filters through this process could be problematic. So we settled on purchasing an Envo filter, which is sold online for $2.50. These filters are readily available for purchase, which means that it would be easy for us and also future users to use throughout this process. This was a huge main body design constraint to ensure that the mask fit the filter and also sealed around it properly. To achieve this, the front face had to curve in only one axis rather than the two axes that normal N95 masks curve in. And the mechanical structure to hold the filter in place is two cages that are 1 millimeter apart with small cylindrical posts to secure the mask in place. This tight fit seals very well to hold the filter between the front and middle stages of the body.
Now, to be able to replace this filter and the cannula and take it in and out, we decided to create a simple hinge and latch mechanism that allows the mask to open from the front and insert and replace the filter and the cannula, and then simply just fold back up and close with a latch. You can see it on the right side there, where the hinge is the left picture and the latch is the right picture. Next, we needed to seal the filter. Once it's in its cage, we needed to ensure that no air was leaking through. So the gap in the filter door, we sealed it with an EDPM hybrid closed cell foam. Through a course of testing, we discovered that 1/16 inch thickness was preferable. We chose this foam because of its deformability. We also needed a way to test various subsystems of the mask through the prototyping process. To do this, we decided to go with the Allegro Bitrix test kit, which is an OSHA standard for testing proper sizing in a respirator. For us, we use it to test various subsystems to make sure there weren't any leaks. The way this test works is you put the mask on your face, and then you put the yellow fume hood, seen at the bottom right, over that. You insert a Bitrix chemical through a tube on a small hole in the fume hood. If you can smell the chemical, that means it's failed. That means there's a leak somewhere in your mask. If you can't smell the chemical, that means it's filtering properly and you passed. To isolate any part of the mask we wanted to test, we would place duct tape over the parts we weren't testing to ensure that they were sealed and to ensure that no air was going through those sections.
So we'll jump to the most novel concept in the project, which is the cannula integration. Firstly, the cannula needs to be placed in a comfortable position that follows a normal cannula tube routing. We also didn't want to split the cannula because we didn't want to alter an existing biomedical device. So we knew that we would need two parts to come together to seal the cannula in between them. So this means that the cannula must enter through a separate openable compartment in the mask. This compartment must seal to an N95 standard without crushing the cannula tube, and we also need to be able to accommodate different sized cannulas.
To be able to insert and remove the cannula, we'd be able to open the second door between the back and the middle of the mask and then close it again around the cannula tube. The gap created by this door needs to be sealed as well. So the gap around the edge of the second door is sealed by a foam gasket very similar to the filter seal. And this seal did in fact pass the Bitrix test, but the harder part of sealing this connection right here is going to be to seal around the cannula tube itself. The initial concept for the cannula seal is like two C shapes that come together to form one gasket. And we chose a closed cell foam for this as well due to its deformability. The simulation in the bottom right shows kind of how these two seals come together, as they need to seal around the rigid cannula, and each part of the seal needs to also seal to itself. This concept looks promising, and we need to determine how to make the foam seal, and we needed to like see this experimentally. So we considered 4 foam thicknesses for this. We considered 1/16 inch, 1/8 inch, 3/16 inch, and 1/4 inch. So to test the 2C's seal design, we made a fixture that kind of looks like an AirPod case that can be seen to the right. The 2 halves of the fixture met at a circular hole, and the cannula tube passed through the hole, and a gasket from the 2C's filled in the spots between the seal and the hole. The seal was tested by holding the fixture underwater while blowing air through the tube, and we visually inspected for bubbles. And if we saw bubbles, that meant it didn't seal. If we did see bubbles, that means it didn't seal. If we didn't see bubbles, that means it was working. And through this testing, we determined that the optimal thickness for this foam was 1/16 inch. So we saw that for low pressures, this test worked. And for higher pressures, we noticed bubbles in a corner closest to the cannula where Alex is pointing. This wasn't a huge cause for concern, as we expected that the exhale valve would really alleviate any pressure that's in between the mask. So this proved the concept and showed promise for the current design and material choice. The sealing test proved that the seal worked under stable test conditions and under like a simple geometry. But when this test was implemented, when this seal was implemented in the mask, it failed the Bictrick's test and it leaked. So we issued the angle that the tube crosses the mask body and the non-ideal cross section where it passes the mask made it so that the gasket was loaded uniformly, and we believe that's what opened up small gaps and broke the seal. Part of the issue was the foam's elastic deformation. We believe that just the way that this mask deformed, it deformed altogether, and it opened up little gaps that air was able to get through. And we think that it was just the more complex geometry that kind of made this happen. The solution for this was to use a seal that deforms plastically. So for the sake of the Bictrick's testing, we used a putty that can be seen there. And once this putty was used, this passed the test with flying colors.
Another aspect of the mask that we had to address was the universal fit, which accommodates for different size heads and different shapes heads. So the face seal and the adjustable strap fall into those categories. For the cross-sectional geometry of the face seal, we decided to create compliance through geometry. So we created a flared structure similar to how swimming goggles seal to a user's face. We quickly realized, though, that the outward flare of swimming goggles would increase the projected surface area of the mask on a user's face, so it would interfere with the jawline and the eyes. So we switched to an inward flared cross-section similar to a 3M respirator. To mold the face seal, a negative was 3D printed, seen on the bottom right, and was used for injection molding a skin-safe silicone rubber, this Dragon Skin Shore 30A. The face seal was then secured to the main body of the mask so it could be tested and tightened to the face using the adjustable strap and toggle stop, which are an easy touch point for users.
As mentioned previously, the target audience for this mask often has difficulty expelling carbon dioxide, which makes the exhale valve in the center body component essential in our final design. While this makes it easier for the user to breathe out of than an N95 filter, with COVID concerns, the team still wants to extend protection to those around us. The addition of an exhale valve cover to the outermost part of the mask provides this external protection as a normal cloth mask would. This demonstration video shows how to open and close the latch and hinging mechanism of the mask, insert the replaceable N95 filter, cannula tubing, and exhale valve cover, and adjust the toggle strap to the user's fit and comfort.
The final cost of the mask ended up being $22, and the breakdown can be seen to the left, with the replaceable filter being $2.50. To bring down this cost in the future, we would use injection molding instead of SLA printing, and parts will be bought in bulk. We predict this would bring down our final model cost to around $10 to $15, which sits well under our desired cost point of $20. Thank you, everybody. We hope you enjoyed, and we'll be happy to take your questions now. Since there's really not too many people asking questions, feel free to just shout them out or type them in the chat if someone's already talking. Anything works.
Shout them out should work pretty well.
Yeah, I've got a question I can ask. First, I want to say great job on your presentation, and thank you for sharing this all with us. It was very interesting, and I like your final design a lot. Yeah, so I guess one of the questions I have is sort of with regards to reusability. There's sort of two parts to it. So the first part is like cleaning of the mask in between uses, and like what's the plan for that? And my next question is with regard to the foam gasket. Like, have you done any sort of life cycle testing on that to make sure it won't like degrade and you know, not perform properly over multiple uses?
For the cleaning, the plastic body can easily just be wiped down with like an antibacterial cloth, a disinfectant wipe. It's very robust. In terms of the life cycle testing, we really haven't tested the long-term life plan. That's part of the processes mentioned in the cost breakdown of finding bulk parts that really could be suitable for the mask.
Okay, great, thank you.
I had a question. Well, first of all, I just want to say nice job. There's a lot of thought that went into this, and it's clear that each component, each subsystem was very well thought out and executed. I had a question about donning and doffing the mask. You know, what the order is for a user to put the mask on their face, to install the cannula, and sort of how that process flows.
Right, I can take this question. So the way this would work is they would loosen the adjustable face strap and put the entire mask on first, and then adjust the strap so that back part with the face seal is close to their face. And then they would open the latch, insert their cannula, insert the filter, and then close it all at once. So does that answer your question?
Yeah, is that something that one person can do without assistance, or do they need to be in a mirror, or how easy?
Yeah, so yeah, in physical testing, it was a little bit tricky at first, but once you got the hang of it, you're good. So maybe a little bit of help or using a mirror for the first couple of times, but after they've done it, they should be all set.
And what environments do you typically expect this to be used in, and what usage are you targeting?
Sorry, can you repeat that again?
Just had a question about the users that you're targeting, and also the environments that this would be used in. Is it going to be used in a hospital setting or an at-home setting?
Someone else want to grab this?
Yeah, I can take this. I think we expect this to be used in an everyday setting. You know, I don't think this is like supposed to be specific for hospitals. You know, this is supposed to be for people with COPD or other diseases that would cause them to wear nasal cannula just to wear around the house, to the grocery store, you know, wherever they would need protection or they feel they would need protection.
Cool. I have a question. You guys mentioned that for cost purposes and for scaling up with manufacturing, you'd probably shift the body of the design from SLA 3D printed to injection molding. Do you have thoughts on what material you might choose when going to injection molding, and any particular reasons why you might choose that material?
We don't have, well, we have a list of specific materials pointed out, just standard plastics, really. It was proven through our calculations that there's really no risk of the plastic breaking. We don't need a very strong plastic, so we would really aim towards any plastic that's cheap, that's easy to manufacture, and that's, of course, skin safe.
Cool. And then how about design considerations going from SLA to injection molding? Any particular aspects of, I don't know, whether it's the hinge or the part where the exhale valve is, would anything have to be adjusted to accommodate the limitations of injection molding?
Yeah, I could probably take this. I think the hinge would definitely be an issue there, as well as the latch. Currently, it's just a solid body that we realized we had to cut open and epoxy together to get it to work properly. So maybe inserting some snap fit pieces into the latch itself so assembly is easy. And either a slide in the injection molding tooling or something like that for the hinge body itself.
Awesome, awesome. And then shifting gears just a little bit, one question on the actual kind of the details of the N95 designation of the mask itself. Is there an association, and I really don't know what the answer to this is, with particle size to N95 masks, a specific particle size that's meant to be filtered out?
Yes, there is. The Bitrix test it's an aerosolizer, and when you spray it, it generates particles of that size that the N95 is spec'd out to filter through.
Gotcha. And that was my follow-up question is regarding the size that N95 rating is for. Did your test incorporate that? So you answered that one in the next one. Perfect. Cool. All right, I can let someone else ask a question.
I'm going to see, Connor, do you want to go into also like validation stuff, the OSHA things that you looked into as well? I don't know if that kind of ties into that question.
Yeah, I can go on that. So we mentioned the Bitrix test, which is great for rapid prototyping. But when the whole mask comes together, it will be tested through a particle counter device. It's just placed on a body, and there's a tube that measures the particles going in and measures the particles going out. And it's as simple as, did 5% of the particles or more go through? If so, it fails.
Right, that's the N95. Gotcha.
Hoping I could elaborate a bit on the exhale valve. I didn't quite understand how the seal is maintained there with the N95 seal, and how other N95 masks deal with exhalation as well.
Yeah, do you want to take this, Molly, or shall I?
You can grab it, that's fine.
Okay, I wish I could pause that video. So on this picture here, below the exhale valve, there's a small lip, similar to the lip that runs around the whole edge of where the filter sits. So when the two doors come together, the filter's pinched in between, and that's what creates the seal between the front and middle halves. And then the exhale valve itself, the structure for it is sunk into the mask a little bit, so that keeps the silicone piece sealed to the body of the mask. And that's something that we modeled off of an existing exhale valve we purchased online and looked at how it was made and actually harvested this little silicone piece from that exhale valve and copied the dimensions pretty much exactly. And then this exhale valve cover, which I don't know if that's where some of the confusion was as well, is once the door is closed, this just slides over it, but isn't meant to be sealed at all. It's supposed to kind of act as a surgical mask does, where it's not a perfect seal for the expelling of particles, but it's still better than not wearing a mask at all, as many studies have shown through this whole COVID fiasco.
So is the exhale valve somehow a one-way valve? Or?
Yeah. So it's mounted in a way that if you're inhaling, it's suctioning pretty much to it makes contact pretty much all the time to the main body of the mask, unless you're expelling oxygen, and then it pushes it out. Yeah.
Is that what is typically used in other N95 masks?
Yeah, that's what the ones on these, I don't know, we have it somewhere. Oh, this is in the beginning. Yeah, this here. So this is, you can kind of see the yellow parts in there, which is that exhale valve on the inside of a mounted piece.
And is the exhale valve cover just, based off of like a cloth mask design for the purpose of, okay. Nice. Also, I do have another question, and that is regarding user testing. Did you have any, did you do any user testing with anybody who actually wears a nasal cannula regularly, or have any conversations with someone to get their input? And if so, what sort of feedback did you receive?
Yep.
So go for it.
Let Connor take that one.
Okay. Yes, we were able to talk to people who use cannulas, but unfortunately, due to COVID concerns and safety concerns, we weren't able to test it. There are also concerns with there'd be a lot of approval to go through of putting like a fully sealable mask on someone who may have trouble breathing. And so for the sake of this project, we didn't test it on anybody, but we did send out a questionnaire that gathered a bunch of data on like cost, comfort, and whatnot through cannula users, and we were able to interview 2 separate peoples who wore cannulas, including the sponsor of this project.
And yeah, that I'm glad you were able to get that feedback. I'm sure that was really helpful. Were there any, like, can you name an example of a design choice that you made that was directly affected by that user feedback that you received?
Yeah, I think the first one that comes to mind is that we were deciding whether we wanted to install a cannula inside this mask or allow users to use their own. And after talking to people, we realized that they really wanted to use their own cannula. You know, they didn't want to have to take out theirs and throw in a new one and attach it and such. So I think that was probably the biggest one I can think of.
XL valve too, I think. Dispelling CO2. Yeah.
Great. Yeah, that sounds like really important feedback to be getting from your users. So that's great.
I had one question on, oh, sorry, Jesse, go for it.
Just would you mind flipping to your requirements slide in?
These ones here, or okay.
Okay, so I was wondering how you assess comfort as it is one of your requirements, and also I was curious about the weight of this entire assembly and how that relates to comfort.
Anyone want to take this?
So for how we assess comfort, it's a good question. I think mostly just in the face seal was kind of how we assessed comfort. We kind of used, like, we looked into how other seals of this type would use, like especially the swim goggles, and we determined that like it's called dragon skin would be like a smooth on, be like a comfortable seal to use like around the face, and I guess that's where it's going to be interacting with the patient the most. Also in the strap placement, we moved the straps once because we found that I believe that they were uncomfortable to the users where they were, and they were also blocking the cannula hole. So moving those was also a human factors consideration. And then what was the second part of your question?
The assembly weight.
The assembly weight, yeah. I don't think I don't have a number off the top of my head, but I don't believe it was, I mean,
it's very light.
I was gonna say, we've had group members wear this and it just never came up. So I wouldn't say that's an oversight. We just don't believe it. Like, I think we just didn't find it to be an issue. But yeah, maybe for some users, they could have found it heavier. I don't believe they would, but I think Alex and Leah touched the mask more.
Yeah, I have it in my hands here. I don't have a scale on me, but it's quite like, you know, I don't know, I can throw it around pretty easily. I'd say it's less than a pound. It's pretty light. And in terms of comfort, because Leah and I were the ones who were wearing it mostly, a lot of it was just any pinpoints that we were feeling. Unfortunately, we couldn't send this out to multiple users because we would have loved to have a varying array of faces to test this on to really see if there's any pain points. But we weren't able to do that as much. And I think that comfort requirement was more so for cannula users, which kind of fell apart in testing during all of COVID. So.
Were there any thoughts to if a user accidentally maybe like didn't have their cannula tube in the notch with the foam, so just user error when closing it, kind of think along the lines of like PFMEA. What happens if the user accidentally misaligns or miss the tube and they go to close it? Is there potential there for user error that could result in leak? Or is kind of built into the design? It's really only going to close if the tube is in the right position, or what kind of failure modes might exist, and what parts of the design are kind of combating those failure modes?
Molly, did you want to grab this one?
Sure. So there are a couple of geometry constraints that will most likely prevent human error. First is that notch to put the cannula into. We believe that if you were to, for some reason, miss that point, either the mask wouldn't fully seal or it would completely cut off the cannula performance. You wouldn't be able to get any air in and out of the tubing. So it should be very obvious to the user pretty immediately that something's wrong and they need to move the placement of that. As far as the other seals go, we are pretty confident with the latching mechanism providing enough force on the foam. However, we did notice a little bit of issue on the sides. There's obviously going to be more force towards the latch at the top of the mask. So in future iterations, we would likely add some additional closure points on the sides of the mask just to ensure that seal goes all the way around. And as far as the filter in the front of the mask, we specifically designed this filter cage around this Envo N95 material. The reason for that is to prevent the user error. So we didn't want anyone taking an existing mask and having to cut it up or make any alterations to it. We wanted this to be simple and straightforward. And this filter is a very specific geometry, particularly with the cutout for the exhale valve. So it should be very clear to the user how that gets inserted. There's not really another way to do it. And we've added an additional gasket, an additional foam seal in that filter cage as well, just to really make that robust.
Cool. Yeah, that definitely answered my question. Thank you.
What about the seal around that cannula? There was mention of a putty that was used to make that seal. Is that something that was intended for final products or just more of a concept?
Yeah. Sorry, I didn't mean to cut you off.
I was just wondering if the user was if that was part of the use instructions for the end user, or if it was more of just a proof of concept that you were testing for R&D purposes.
Yeah, so I think that was much more for proof of concept. We noticed that when we Bitrix tested this seal that it wasn't performing like as needed. There were gaps. We found that this putty was a way to kind of prove a concept that if there was a more deformable material in that seal, that it would conform to that. And especially given that weird geometry that ended up being necessary. But yeah, the putty for the sake of now was just a proof of concept. In later iterations, we would either make this geometry a little more simpler so that it closed similar to how the gaskets and how the foams and how the filter seals did, or B, move to a soft rubber, kind of like a silicone that would kind of take the shape as the putty did. But yeah, for now, the putty was just a way of kind of proving that this concept could work.
And I think you mentioned this, but what's the range of cannula tube sizes? Is there a couple kind of off the shelf, like a range that of commonly used cannula tube sizes, and they don't necessarily get larger or smaller than a certain amount?
I don't think there's like I think they all hover around like 3 millimeters is what we found. If someone else is remembering,
there is a range.
Yell it out.
Yeah, I don't remember the range off the top of my head.
I think it was
a
like
range of sizes we found through our research talking to users as well as experts in the medical field that there are 2 typical sizes for the nasal cannulas, and they are basically dependent on the flow rate that a user needs. So there is one size tubing that is most commonly seen, particularly for people with respiratory illnesses based on the flow rate requirements they need. So we did base our design mostly around that tube sizing. The difference in diameter is pretty small. If I remember, it's on the order of 0.5 millimeter or less. And we decided that with this deformable foam seal that we would be able to accommodate multiple sizes. As Mikey said, moving forward, if we were moving towards a more deformable material for that seal, it would definitely be easier to accommodate different sizes. However, for the scope of the project, we found it easier to focus our design specifically towards one size of tubing, just to prove out the concept.
Cool, that makes sense.
What do you see the next steps for this project to look like, either theoretically or in real life, if you're actually planning on pursuing any next steps?
So I think we've hit over, Mikey on the last question talked about how we're going to upgrade the cannula seal. But the other side of that is the cost next steps and sort of material sourcing. Like we mentioned, we would need to alter the design a little, especially the hinge part, for proper injection molding. And then we would need to really look into parts. I believe you asked the question before about life cycle testing. We would do pretty in-depth life cycle testing of the foam. We would, we know how long a filter lasts. And so it's really just a process of like manufacturing, part selection, everything, just really optimizing it.
And then definitely the testing that you talked about earlier about verification, getting to the FDA would be a massive concern as well.
Right. Yeah. And that happens after. It requires that you use, like, you can't change the design once you test it. That would come at the very end. Once everything is decided, parts are decided, the design is not going to change. You would do the particle counting testing.
Nice. And do you have any plans to actually do any of that or hand this design off to someone? Or like are you working with anyone to try and get any of those next steps? Or I'm just kind of gonna stop after Capstone is over, which is also.
So if we were, I can grab this one. So if we were to move forward, a lot of this idea is actually patented under a company called SleepNet, which is where we got the Envo filter from. So the novel part of our concept is the cannula seal. So if we were to move forward, we would basically present this concept to them and be like, hey, like you can try to make a mask with this sort of cannula integration.
Cool. Very nice.
Was there a specific, was there a sponsor for this project or a specific end user that brought this idea to Northeastern that triggered this project?
Yeah, so our Capstone advisor, Carol, she has an aunt who actually wears a nasal cannula who brought this idea to us. And so we got to talk with her in the beginning of the project to kind of get her input, and obviously having Carol as a resource through the entire thing was really helpful.
That's great. Having that direct voice of customer feedback into the design is great. Any chance, or did you get a chance to test it with her, or any chance that maybe she could try and test out a prototype?
Right. So obviously, as we mentioned during the presentation, with COVID concerns, we didn't get to send it to her because we only had time to really work with one prototype. But if we were to continue in the future, we would hope to make multiple prototypes and be able to send it to her and to other nasal cannula users to get better feedback.
Great.
Do you anticipate that this design would be a one size fits all? Would you have to have multiple sizes for different populations? And would this also work in a pediatric setting?
So that's what the Universal Fit was hoping to do with the face seal. Pediatric, I don't think that this would fit them. It is quite large. We might have to have a separate variation for children. But for adults with similar shaped heads or sized heads, the face seal is meant to accommodate that variation between face to face. So we could use a little bit of tweaking on that and using it, testing it on more users just to confirm that going forward. But that's what those two components were for, the face seal and the adjustable strap.
Did you size the envelope of the shield?
What's that?
How did you size the profile or
the face seal?
Yeah, how did you use human factors data, or was it sort of just testing it yourselves? How did you choose the dimensions?
Yeah, so the first iteration, we used a 3D CAD head that we were able to find online and took the profile of like a mask that you would see, like the Envo mask or whatever the filter would project onto that face, and then created like topology based off of that. So the first mask was actually very, I guess it had a lot of pinpoints and pain points because it was shaped perfectly to this CAD model's head. So for the second iteration here, a lot of this was based off of just a circular curve, and we did have a humans factor book that Molly had access to, but we weren't able to find too much on this face conformity stuff. So I think the next step with the face seal would be to kind of blend the two, first iteration and second iteration, because this one could definitely use a little bit more human geometry rather than just a circle cross section, but the other one was way too much. So hopefully the third, final charm.
Do you know if there already exists like a respirator or something with a similar sealing technology that is a universal fit? Just because it it seems like it would be a little bit tricky to nail down because everyone's
Yeah.
faces are very differently sized as we're learning this year.
Yeah, I'll show a picture. We have one pulled up actually. So this is the 3M respirator, which it's one of those respirators that have the 2 filters on the side here. So I think one of the things we would need to do is lengthen the whole mask in terms of like the vertical axis, and have it go underneath the chin, similar to how they have it here, because that's what this cross section does.
Cool. So you know it can be done.
Yeah, yeah.
The off-the-shelf filter that you are using, where is that used currently?
That's go
Yeah,
ahead.
they make their own N95 mask. There it is. Yeah. They sell the filters separately, but they also sell an N95 mask. That's they market it to construction workers. So we took their filter and integrated it into our mask.
And is that a one-size-fits-all mask?
That's what they advertise it as. Yes. Their seal is actually, they have a patented product called air gel, I believe. And it's this very unique like gel inside of a plastic bag feel. It's hard to describe.
It's like a polyurethane. Yeah, polyurethane gel.
And that's how they go about their one-size-fits-all seal.
Cool. I'm just curious, how did COVID impact the timeline of the project? Or were there any things that altered the timeline? It's very interesting. It is very specifically a COVID-focused project, and I can imagine, as I've seen in the previous presentations, there was a lot of adapting the team had to do. So how did that affect just the different aspects of the project and the design?
Yeah, so we actually ordered, we're in like 4 different locations. So we all ordered ENVO masks right in the beginning of Capstone 1. So we were able to get our hands on those N95 filters early on, which was good because they took like a month to get them all shipped to us. And then we did have to push back our physical prototyping because we didn't have access to Boston and to the Capstone lab until like mid-October, towards the end of October. So we had to do a lot of our like kind of validation CAD work and stuff more early on, and then incorporate the testing a little bit later.
Gotcha. A really great job, guys. This looks awesome and in a very specific need pinpoints. So excellent job, great design, great presentation.
Thank you.
Thank you.
Thank you.
If we reach the point where the jurors have asked all the questions that they would like to, or at least for now, there are a couple in the chat from the rest of the audience. Jurors get precedence, but.
Yeah, feel free to go to the chat questions.
So we have any thoughts on other variations for different patient populations in the future? I think we might have addressed that in the questions already.
Yeah, I think oh my God, I can't say the word. Children may need a different one. Pediatrics.
And then do we foresee it being available anytime soon? So again, as we kind of said, that we couldn't, due to different patents, we wouldn't be able to produce this on our own. So this would be something that we would have to kind of, present to SleepNet, and they would have to accept it and work through their own manufacturing. So unfortunately, no, we wouldn't be able to control it being available.
Yeah, they have a patent on reusable N95 masks. So that kind of kills a lot of our ambitions.
If there are any other questions, we're all ears.
Comments, concerns?
There was a comment about MRI compatibility. I'm not an MRI expert, but I believe metal is one of the things that can't necessarily go into an MRI machine. We do have a small bit of metal that pins the hinge together. You can see it at the bottom right there. If we wanted to make this MRI compatible, I'm certain the metal could be replaced with any other objects.
Yeah.
There's also metal in the, there's a metal wiring in the cover, the exhale valve cover, and there's a small spring in the toggle stop as well. So those are parts that would have to be
Yeah, I want to commend you guys on a really nice job. This looks very finished. I think it addresses a real need, one that I hadn't really considered prior to this presentation, but makes complete sense. So I want to congratulate you guys on a really nice job. Nice job on this project. I had one last question, which was you mentioned that you used injection molded silicone for the seal around the face. And I was just curious what takeaways you learned from designing an injection molded part, an injection molded silicone part specifically, and what you learned from that experience.
Yeah, I can speak to that. I did a lot of research prior to creating a mold. So I had never done any molding previous to this. So learning like what a core and cavity was a huge first step. Between our first iteration and our second, I added a few supports to keep the core and cavity locked together, vertically in the axis that we want it to, because previously we had so much more geometry that the two halves stuck together well without those pins and circles. I don't know the technical terms for them. And then we also accommodated for different size syringes to inject. At first, our entry hole was very, very small and we were having troubles injecting and we didn't have enough exhale vents so that the air could get out. So we were able to accommodate those and change that in the second design, which is what made it come out so much better as the second one.
And something we actually incorporated, we would vacuum the silicone beforehand every time to release the air bubbles. But something we actually incorporated on the second molding was that after it was already in the mold, we put it under a light vacuum that was able to release just the small amount of air bubbles that came through the actual injection of the liquid silicone into the mold, which went a long way to helping that part.
Yeah, it's a really good learning experience.
Are there any more questions?
Yeah, I have one.
Okay.
Also want to close by saying, yeah, I think you guys did a really great job. You focused on the user needs, and it seems like you kind of let that guide all of the project, which I think is as it should be. And yeah, your final design looks, it was really well thought out and well executed. So nice job, and thank you for sharing with us. I guess I just wanted to ask if there was anything else you wanted to highlight that you haven't been able to bring up so far, or if we covered it all.
Can't think of anything off the top of my head if anyone else has something.
Yeah, I think we kind of covered all the main components of the design.
Mm-hmm. Okay,
Yeah.
Great.
Thank you.
I'll get personal here for a second. We said we talked to two people who use cannulas. One was our advisor Carol's aunt. The second was my dad, who also wears a cannula, and he was a huge help in sort of telling us about the comfortability of the cannulas, rubbing against the skin, and a bunch of different stuff. So I guess thank you to him.
Mm-hmm.
And to Carol for being a good advisor, a great advisor.
Yeah.
This is very helpful through this whole process. So
Yeah, Carol's been the best.
Thank you.
All right. Well, it's been a pleasure working with you all. And I also want to take the time to thank the jurors for being here. We really appreciate your contributions and your insight and wisdom, Jesse and Julia and Andrew. Thank you.
Yeah, thank you all.
thank you all.
Thanks for the invite.
Thank you for coming. Really, really appreciate it. You guys had awesome questions.
Yeah, really nice. Best of luck to all of you as you move towards your future careers.
Thank you.
All right. Well, let's close it out with that. It gives the jurors a few minutes before the next place they have to be.
Awesome.
Okay.
Thank you. Nice job again, guys, and good luck with finishing up your senior year.
Thank you.
Good. Thank you.
All righty. Bye.
Bye, everybody.
Bye-bye.